Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering a whole new topic called command injection. Just like with the other theory videos, this is pretty much a brain dump of everything that I know about command injection attacks, and so it's going to be a long one. But by the end of the video, you'll have all the fundamental knowledge that is required to complete the 5 hands-on lab exercises that we'll be covering in the next upcoming videos. Alright, let's get started. The agenda for today is to first cover the technical details behind command injection attacks. So what is a command injection vulnerability? What are the different types of command injection vulnerabilities? What are the conditions that must be satisfied for a page to be vulnerable to command injection? How common are command injection vulnerabilities? And so on. Next, we'll cover how to find command injection vulnerabilities from both a white box and a black box perspective. So if you're given an application and possibly even the application source code, how would you approach testing the application in order to determine that it's vulnerable? Once you've found that the application is vulnerable to command injection, how do you exploit it to achieve your end goal? Then we'll end the presentation by covering the different techniques that you can use to prevent or mitigate command injection attacks. Okay, let's get started with the first section, which is what is a command injection vulnerability. Command injection, or also known as OS command injection, is a vulnerability that allows an attacker to execute commands on the host operating system through the vulnerable application. So in past videos, we talked about SQL injection, where an attacker is able to inject SQL code into a database. Now, command injection is really similar to that, with the exception that instead of injecting SQL code into a database, you're injecting system commands in the host operating system. Let's take an example to better understand this. Imagine you have a user, Alice, a web application that is vulnerable, and a web server that the application is running on. The web application is used to configure routers, and so it gives you the ability to ping IP addresses through the application in order to make sure that an IP address is up and running. And the way to do that is you, as a legitimate user, Alice in this case, pings an IP address that Alice wants to check is up and running. And in this case, that's 127.0.0.1. And then Alice clicks on the ping button, which initiates a request to the web server and executes the ping command. So think of it as if a command line is being opened up, and then the command ping 127.0.0.1 is run on the command line. Now, all ping does is send an ICMP echo request to the device on the network, and if the device is up, it sends back an ICMP echo response. And so what happens is that the ping command is run, and then the response of the command is outputted in the web application. So Alice over here can see that the address that she pinged is up and running because she sees the response of the ping command. And you could see over here the time to live is 64, which means that this is a Unix system because that's a default time to live for Unix systems, and it's not for Windows. Windows is about 127. Okay, so this is a normal use case of how the application functions when used by a legitimate user. However, what happens if an attacker gains access to this application? Well, if there's no server-side validation on this parameter over here, then there's nothing stopping an attacker from entering system commands and having them run on the underlying web server. In this case, the attacker is running the cat command to output the contents of the etc passwd file. So the reason we selected the passwd file over here is because it's a world readable file. And so regardless of the user context that the web application is running with, it would be able to read that file if this is vulnerable to command injection. And so when the attacker clicks on ping, what's going to happen is it'll run the ping command on the IP address 127.0.0.1, and then it'll run the command cat/etc/passwd, and it'll output the contents of both commands in the web application. So you could see over here, that's the output of the ping command, and over here, that's the output of the cat command, which outputted the passwd file. And so this allowed the attacker to exfiltrate information from the web application. And this should highlight that this type of vulnerability can have really serious consequences to your organization if it were to be exploitable. Because not only can you exfiltrate data from the system, using this vulnerability, you can actually add a line of code that gives you a reverse shell on the system, which gives you complete remote code execution to run any command that you want on the underlying web server. Alright, from a backend code perspective, how can this vulnerability be introduced into your application? Well, if you allow execution of operating system commands using functions like the exec function, and you do not validate client-side user input, then you're vulnerable to command injection. So if we look at our example over here, we've got line number 6 running the exec function, which allows you to run system commands, and it takes in 2 parameters, the CMD parameter, adds a space to it, and then it takes in another parameter called the arg parameter. Now, in order for an application to be vulnerable to command injection, it needs to satisfy 2 conditions. The first one is that it uses a function that can execute system commands, which is satisfied over here, and the second one is that the parameters to this function are user controllable, so they come from the client side. And this is also satisfied over here. So if you see the CMD parameter over here, it's set in line number 4, which is taken from the request that is coming from the client side. And also the arg parameter over here is also taken from a request that is coming from the client side. So essentially all an attacker would have to do is set the command parameter to cat and then set the arg parameter to /etc/passwd, and then the attacker is able to exfiltrate data from the system. So there's nothing stopping the attacker from entering malicious commands in the client-side parameters and then executing it on the server. Alright, so we talked about the technical details behind command injection vulnerabilities. Now let's discuss the different types of command injection vulnerabilities. At a high-level overview, there are 2 types of command injection. The first one is in-band command injection, and the second one is blind command injection. They both work almost exactly the same, with the exception being if the response is returned back to you in the application or not. So if we take in-band command injection, it consists of an attacker executing commands on the host operating system through a vulnerable application and receiving the response of the command in the application. So the response of the command that you run is reflected back to you in the application. And we saw that in the previous example. When the user entered the IP address in the parameter, the response of the ping command was reflected back to the user in the application. Now, in blind command injection, it's a little bit different. So it consists of an attacker executing commands on the host operating system through a vulnerable application. However, the application does not return the output from the command within its HTTP response. So think of it as having the same example that we had last time, except the output of the ping command is not returned back to you in the application. This is obviously a much harder vulnerability to exploit than in-band command injection because you don't get the response from your command. However, there are techniques that you could use in order to validate that an application is vulnerable to blind command injection and then to exfiltrate data using this type of command injection. And we'll learn about it more in the next coming slides. Okay, so in the past couple of slides, we discussed technical details behind command injection vulnerabilities. Now let's talk about the impact of such vulnerabilities. Usually when I'm talking about impact of a vulnerability, I refer to the SIA triad, which is confidentiality, integrity, and availability. Now to understand that, let's go back to what we said. We said that usually when it comes to command injection attacks, you could run arbitrary commands. So you get remote code execution on the operating system. And so, just by definition of what remote code execution is, confidentiality, integrity, and availability would be affected at the highest level. Confidentiality is affected because a command injection can be used to view sensitive information, just like we saw with the passwd file. Integrity is affected because a command injection can be used to alter content in the application or files on the host operating system. Availability is affected because command injection can be used to delete the entire file system and so deny access to the application to users. And therefore, it affects all three of them at a maximum level. And this is a pretty serious vulnerability. So usually when you find it, you'll see that confidentiality, integrity, and availability are all rated at high, which makes the CVSS scoring critical. Okay, so that was the impact of command injection vulnerabilities. Now the question is, how common and how critical are command injection vulnerabilities? One way to measure that, and it's not bulletproof, is using the OWASP Top 10 list. So for those of you that have not heard of the OWASP Top 10 project, it's essentially the list of top 10 most critical security risks in web applications today. It's updated every couple of years. So you could see over here, we've got the 2013 list, the 2017 list, and the 2021 list, which only came out a few months ago. And as you can see in the 2021 list, we've got command injection falling under the broad category of injection, which is the third most critical risk to web applications today. And this broad category has been around for a while, so you could see in the 2017 category, it was number 1, and in the 2013 category, it was number 1. Now, I mentioned this to be a broad category because command injection is just a certain type of injection that falls under this category. And so when you're answering the question of how common are command injections, you can't really use the OWASP Top 10 list to answer that question because injection covers all the different types of injection, not just command injection. However, we did discuss the second part of the question, which is how critical are command injection vulnerabilities, and we saw that in most cases of command injection, you could gain remote code execution, and so these vulnerabilities are considered to be really critical. Alright, in the past couple of slides, we discussed what command injection vulnerabilities are, the different types of command injection, the impact of command injection, and how common and critical command injection vulnerabilities can be. In this section, we'll discuss how to find command injection vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing the application to see if it's actually vulnerable? And before I cover that, it's worth mentioning that the methodology used for finding command injection vulnerabilities differs from one person to another person, and it's usually developed by experience. So just because I give you my own methodology doesn't mean that you have to follow it to the letter. Instead, I would recommend that you take what is useful for you from it and then build and add on to your own methodology as you gain more and more experience pen testing web applications. And this statement applies to finding all vulnerabilities, not just command injection vulnerabilities. Okay, with that out of the way, I've decided to split this into two categories depending on the perspective of testing. And the two categories are black box testing and white box testing. For those of you that have never heard of these terms before, black box web application pen testing is when a tester is given little to no information about the system. Usually the only information that the tester has access to is the URL of the application and the scope of the engagement. Whereas for white box web application pen testing, it's the complete opposite. The tester would be given complete access to the system, including access to the source code of the application. Now, there's a third category that I haven't included on this slide that is called gray box web application pen testing. This is a combination of both white box and black box pen testing, where the tester is given limited information and access to the system. So for example, instead of just giving the tester a URL to the application, you also give the tester accounts to the application in order to do testing. Now, when it comes to my methodology of finding command injection vulnerabilities, I loop both gray box and black box pen testing into one category, and that's because my methodology is the same for both categories. If I'm approaching it from a black box perspective, my scope will be much more limited than a gray box perspective unless I find an authentication bypass vulnerability. Nevertheless, the methodology for testing command injection vulnerabilities in public and authenticated pages is the same. Now, white box is a category on its own because you're actually given access to the source code of the application. And so the way to test it is completely different from the way you would test an application from a black box perspective. Okay, let's start off by talking about how to test applications from a black box perspective. The first thing that I do when testing an application is map the application. And what that means is I literally visit the URL of the application, walk through all the pages that are accessible to me within the user context that I'm running as, make note of all the input vectors that potentially talk to the backend, understand how the application functions, try to figure out the logic of the application, and so on. And while I do all of that, I have my burp proxy listening silently and intercepting all the requests that I'm making to the application. I would personally argue that this is probably the most important step when it comes to testing an application, so make sure to spend quite a bit of time on this step before moving on to other steps because it will really pay off in the end. Okay, so when we're looking specifically for command injection vulnerabilities, what I will do is identify all instances in the web application where the web application appears to be interacting with the underlying operating system. And now this task in some cases is really simple, like the example that we saw, where it's clearly running a ping command and the response of the command is being outputted to you in the application. And so you know for sure that it's interacting with the operating system. However, in other cases, you'll see that it's not so simple and a parameter is really interacting with the operating system. However, there's no indication from a black box perspective that it's interacting with the operating system. And so in scenarios like this, what you need to do is you really need to map all instances in the application where there's client-side input. Because wherever there's client-side input that potentially talks to the backend, then you could have a potential command injection vulnerability. Now, once I've mapped all the request parameters of interest, then it's just a matter of fuzzing the application with command injection payloads. Now, in these payloads, you'll likely use one of these shell meta characters, and there's quite a few of them that you can use to perform command injection attacks. Some of these characters function as command separators, allowing commands to be chained together, like the first 4 over here that work for both Windows and Unix-based systems. Some of them only work for Windows systems, like the semicolon and the new line. You also have characters that allow you to perform inline execution of an injected command within the original command, like the backtick character and the $sign character. And if you have no idea how this works, we're going to talk about it in the next section. And we also have 5 lab exercises that are coming up in the next couple of videos where you will gain hands-on experience exploiting these types of vulnerabilities. Okay, so once you fuzz the application, you will come across one of 2 scenarios. If it's an in-band command injection, what you need to do is analyze the response of the application to determine if it's vulnerable. So with in-band command injection, the response of the command is outputted to you in the application. And so you're able to analyze it to see if the application is vulnerable. In the example we saw in the past couple of slides, we saw the output of the cat command in the application, and so we know right away that it's vulnerable to command injection. However, in some scenarios, it's not going to be that simple because some users filter certain characters and don't allow you to use those characters. So what you need to do is literally fuzz the application with each and every single character and analyze the response. Sometimes the response will be the output of the command. Other times it might be an error. And so you need to analyze that error to see if that error indicates that it's vulnerable to command injection. And again, we'll see that in one of our lab exercises. Now for the second scenario, which is blind command injection, you need to get a little bit creative because the response of the command is not outputted to you in the application. And so one way to prove that it is vulnerable to command injection is to trigger a time delay using either the ping or the sleep command. So when you trigger a time delay in the application and you say, let's say sleep for 10 seconds, and the application takes 10 seconds to respond back to you, that means it's definitely vulnerable to command injection. Now, this allows you to prove that a command injection vulnerability exists. However, it does not have any impact. So there's no impact to this command injection vulnerability. And the way to get impact is to use one of the following techniques. So you could either exfiltrate data from the application by outputting the response of the command in the web root directory and retrieving that file directly using the browser. So what you would do is, let's say you run the dir command, and then you redirect the output of the dir command in a directory that is accessible through the webroot directory by anyone that is using the application. And then if you see that that file got created and is available for you to download, that means the command injection worked and you could exfiltrate data using that technique. However, if you don't see that the file was created, that means that the command injection did not work. Another way is to open an out-of-band channel back to the server that you control. And this is usually done using Burp Collaborator. We'll discuss it in the next section to see exactly how you can do that. Okay, so that's for a black box approach. Now let's talk about testing it from a white box testing approach. So I don't do pure source code review on applications. When I'm given the source code of the application, I usually perform a combination of both a black box and a white box pen test. And so the first thing that I do, I map all the input vectors in the application from a black box perspective, and then I review the source code to see if I've missed any input vectors through my black box pen testing. Now, after I've mapped out all the input vectors, I review the source code to determine if any of the input vectors are added as parameters to functions that execute system commands. So instead of me having to guess if these parameters are added to functions that execute system commands, all I have to do is review the source code. And if I see any functions that perform system commands, then definitely this should be tested for command injection. And another reason having the source code is really valuable is because sometimes developers do have defenses in place against command injection vulnerabilities. However, sometimes these defenses are inaccurate. And if I have access to the source code, I could just review the source code and learn how to bypass these defenses and then test out my hypothesis. And that's really the next step, which is once a vulnerability is identified, test it to confirm that it's actually exploitable before you present it to the client. Alright, so far we've learned the theory behind command injection and how to find these types of vulnerabilities from both a black box and a white box perspective. The next thing we're going to discuss in this section is how to exploit command injection. This would largely depend on the type of command injection that you're encountering. So we talked about two different types of command injection, an in-band command injection and a blind command injection. If it's an in-band command injection where the output of the command is displayed back to you in the application, then it's as simple as concatenating another command to the command that is originally being run by the application. And to do that, you use one of these shell meta characters. In the past example, we saw that the way we concatenated another command is using the double AND characters and then adding the command that we want to run. Now, depending on the application, you might have to do it differently. So another way that it would work is just using a single AND character or using the OR operator to perform that. It would really depend on how the application works and if there are any inadequate defenses that are put in place that prevent us from entering one of these characters. So that's for in-band command injection, which is really simple. Now you've got blind command injection. That's where the output of the command is not displayed back to you in the application. And so one way to test for that is to trigger a time delay. You could do that using either the sleep command or the ping command. The sleep command only works, I believe, for Unix systems, whereas the ping command works for both Unix and Windows. So if you don't know the operating system that is hosting this web server, then you don't want to use the sleep command, you want to use the ping command. And the way these two commands work is they will essentially trigger a time delay of 10 seconds. And so it'll take the application 10 seconds to respond to you before you see a response from the application. And if it takes 10 seconds, then you know for sure that it's vulnerable to command injection. Again, in the previous section, we talked about how this only proves that there's a blind command injection. It doesn't have any impact from the command injection. And so to prove impact, you could either output the response of the command in the webroot directory and retrieve that file directly using the browser. So we talked about, let's say, running the whoami command, redirecting the output over here to this directory, which is available to anyone that is using the application, and saving it in a file called whoami.txt. Now, if you browse to this directory from the browser and you see that there's a file called whoami.txt, then the command injection was successful and the content of the whoami.txt file will be the output from the whoami command, which is the user context that the user is running with. Now, this just uses the whoami command. We can use any other command to exfiltrate data from the system. Another way to both prove that a command injection exists, and to exploit it to show impact is to open an out-of-band channel back to the server you control. Usually this is done with Burp Collaborator, but it essentially can be done with any attacker-controlled server. The way it works is if you're proving that this is vulnerable to blind command injection, all you have to do is run the NSLOOKUP command on the server that you control. And since you control that server, you would be monitoring the logs to see if the vulnerable application performed a lookup on your attacker-controlled server. And if it did, that means it's vulnerable to command injection. If it didn't, that means it's not. Now, again, this does not prove impact. So if you want to prove impact, what you need to do is essentially run a command within a command. And you could do that using either the backtick characters or the $ characters. And what this essentially does is it runs the whoami command. It appends the response as a subdomain of your attacker controlled domain, and then it performs an NSLOOKUP of that subdomain. So if you're monitoring the logs, you'll see that so-and-so server performed an NSLOOKUP on the output of the content of the whoami command this subdomain .thewebattacker.com domain. And so you essentially exfiltrated data from the system. And again, we have 5 lab exercises that will give you hands-on experience exploiting each one of these scenarios of command injection. All right, so we discussed how to exploit command injection vulnerabilities manually. Of course, we can't end this section without mentioning web application vulnerability scanners, which are essentially automated tools that crawl your web application and look for vulnerabilities. Now, any decent scanner should have the ability to scan for command injection. I personally use the Burp scanner. However, I've listed a few scanners on the slide. Some of them are free and open source. Others are paid but are not so expensive, whereas others are very expensive. And so it really depends on your organization and which scanner you're more comfortable using. However, I do want to highlight it's really important that you automate the finding of command injection vulnerabilities, because you do need to test all the different parameters in the application, which could be hundreds of parameters. And so it's really not feasible that you do this manually. What you want to do is you want to use a scanner that you know for sure tests for command injection, and you want to configure it to ensure that it tests all the different parameters in the application for command injection vulnerabilities. Okay, so we talked about the technical details behind command injection vulnerabilities, how to find them, and then how to exploit them. Now let's talk about how to prevent command injection vulnerabilities. So the primary defense to command injection vulnerabilities is to avoid calling OS commands directly. As an alternative, what you could do is use built-in library functions that only perform the specific task you intended for them to perform and cannot be manipulated to perform other tasks. So for example, instead of using the system function, you could use the mkdir function. The mkdir function, all it can do is create a directory. It can be manipulated to perform any other commands, whereas the system function can run any command on the operating system. And so it's much safer to use the built-in library functions that only perform the specific task that you intended for them to perform versus using a function that allows you to run any command on the operating system. Now, if it's absolutely necessary and required for you to perform OS commands using user-supplied input, then there are 2 layers of defenses that you could perform. The first one is validating against a whitelist of permitted values. And so let's take the example that we saw before. If you really all you need to do is ping 127.0.0.1, so localhost, and ping another IP address, then in that whitelist there should only be these 2 IP addresses, and if you enter one of these 2 IP addresses, then it passes through. However, if you enter another IP address or any other command or character, then the application responds with an error message and does not run your command. That's how a whitelist works. You definitely don't want to use a blacklist, because blacklists are usually bypassed and are inadequate defenses. The second line of defense is to validate that the input is as expected or valid input. What that means is that if you're expecting the user to only enter integers, then you should only allow the user to enter integers. You shouldn't allow the user to enter alphabets, and you shouldn't allow the user to enter other characters. Similarly, if you allow the user to enter all alphabets and integers, well, then what you should do is only allow the user to enter alphanumeric characters, and you shouldn't allow the user to enter other characters in the system. And that's essentially how you would defend against command injection. Again, the primary defense and the most effective one is to avoid calling OS commands directly. Instead, what you should use is the built-in library functions that only perform the specific task that you intended for them to perform. Okay, before we end our video, let's talk about the resources that were used in order to build this presentation. The first one is obviously the Web Security Academy OS Command Injection module. All my videos are dependent on the Web Security Academy that is provided by Portsfigure, and so majority of my content is from there. The second resource is the Web Application Hackers Handbook, which is created by the same people that created the Web Security Academy. So there's 2 chapters there that discuss command injection and how to test for these types of vulnerabilities. And the third 3 links that I have on the slides are OWASP links. So they discuss the technical details behind command injection, how to defend against command injection vulnerabilities, and then how to test for command injection vulnerabilities. And this ends the command injection theory video. Make sure to keep an eye out for the 5 hands-on lab exercises that we'll be covering in the next upcoming videos.